So today is all about inverse functions. Before I get to talking about inverse functions, I want to do just a little bit of motivation. So the idea of an inverse function is to combine a bunch of repeated work that you would otherwise have to do many, many times into doing it once in a slightly abstract setting, and then applying that abstract example in many concrete sets of places. So, for motivation, here's the equation. Let's solve it. X cubed plus 2 equals 1. If you wanted to solve that equation, what would you do?
First subtract 2 on both sides. Because you're eventually solving for x. So you subtract 2 on both sides, then you the first square root, and then it's just the power of like square root of that's like the power of 2 to the power of 3. So.
Yeah, so the cube root is what that's called. So let's take the cube root of both sides. X equals the cube root of -1. And the cube root of -1 is? Just -1. Right, -1 cubed is -1.
Oh, okay.
And -1 times -1 times -1. Two of the negatives canceling out with 1.
Oh, nice.
So that's why I think it is -1. Right, there is that equation solved once. X cubed plus 2 equals -7. Do you think that would take some similar steps to solve?
Probably, yeah.
Tell me, what is the solution to that equation?
Square root of 3. Yeah. The negative square root of 3?
Yeah. Because if you subtract 2 out of the sides, you're going to hit on the cube or that should be.
So far I found the cube root of -3, negative cube root of 2. Any other solutions? I guess you need to subtract that 2 to the other side, right?
Yep.
Cool, what does that give you?
I can do -9.
X cubed equals -9. And what would you want to do next?
Then cube both sides to get x up. So I'll keep it.
So, and yeah, so picture the cube root function in your head. That function is odd. So I can pull that -1 out. Is 9 a number that you just know the cube root of? It's a square, it's not a cube. So I guess like the cube root of 8 is 2, so cube root of 9 is a little bit bigger than 2. But that doesn't matter right now. There's the solution to this equation. In solving each of those equations, we did something pretty similar each time. But in fact, we did like the exact same stuff each time. So here's the point. That's inefficient. Just put yourself in a slightly abstract setting. Solve that slightly abstract problem. Go from there. So there's a slightly more abstractified version. Does that look like an equation that you could solve for x? I think so. You would subtract 2 to the other side and then take a cube root. Exactly the same as the previous problems. X cubed equals y minus 2. X equals the cube root of y minus 2. So here's the point. That now gives you a formula that says whenever you want to solve something the form xt plus 2 equals y, there's the formula for the solution. So let's not solve the equations anymore. Let's just use the formula. If I ask you to solve x cubed plus 2 equals -2, what do you need to do? You could just use this formula, right? And plug in what for y? -2. X equals cube root of -2 minus 2, I guess that's the cube root, of 4. -4. Yeah, I lost the negative sign. Thank you. Negative the cube root of 4. People feel okay about this? Does that make sense? Yeah.
What makes the cube root be negative? Because like on the first one, we didn't have it be negative, but the other ones we did. Why is that?
So, here we have the advantage that I know an explicit number whose cube root is negative. I don't know an explicit number whose cube root is -9. So the best I can do is simplify wherever possible. So the cube root function is odd. So whenever you see a negative inside the cube root, you just pull it out. Just like if you saw y -5 cubed, you would write that as -5 cubed, even if you didn't want to cube 5. Same thing is happening there. Yeah, the only reason it's not a cube root here is because 1 happens to be a perfect cube. That's okay, cool. Nice. So this idea, yeah.
Can I get a new packet?
Maybe. It's entirely possible that I only brought the new packet and didn't bring any extras of the old. I bet you already got a copy. Did you get a copy of this one yet?
No.
Okay. This is what we're doing today. This is what we will be doing next time. Oh, yeah. I have to pay attention to who doesn't come in like 5 minutes already. Anyone else need one? Or I should just hold off handing things out until everyone's here. That would probably be the more reasonable solution. Good. So, this in more generality is what inverse functions are. Whenever you see an equation that looks like f of x equals y, and you want to solve to get x as a function of y, which notice, that's what we did right here. This gives x as a function of y. So whenever you solve f of x equals y to get x as a function of y, you are finding an inverse to the function f of x. So what does that mean? That means for f of x equals x cubed plus 2, the inverse function is given by f inverse, the independent variable is called y right now, equals the cubed root of y minus 2. The new function is f inverse with a little -1 in the superscript. Alright. So that now has like y as the independent variable in a function. Usually we use x for the independent variable in a function. Not that there's anything magic about the letter x as opposed to the letter y, but just in order to follow the usual format, all I change the y back to an x. F inverse of x equals cube root of x minus 2. Cool. People feel okay about what's happened so far? Any questions right now? Let's go through the walk of finding an inverse function. We'll do this a few times today. Here is an inverse function, f of x equal to 3x minus 2. Let's find f inverse of x. So here's the last strategy that we've outlined right now. Take a formula that gives y as a function of x, solve for x, now change the y into an x and the x into a y. It doesn't matter what order we do that, and just in order to emphasize, maybe here I'll switch the variables for. So let's switch the x and y, then we'll solve for x. So if I want to find the inverse to 3x minus 2, I'll write down the equation y equals 3x minus 2. I'll switch the x's and y's to get x equal to 3y minus 2. Is that the first something you could solve for y? Yeah, and now maybe I'll give you one or two options. Solve for y and then tell me what you get. Or does anyone want me to talk through some algebra? Okay, I will talk through the algebra. So, there's the thing I need to solve. I want to get y on its own. That seems like a good boss move. Order of operations says plus you multiply, then you subtract. So to undo plus, I would undo subtraction. Then I would do. So let's do that. Add 2 to the other side. X plus 2 equals 3y. Now say the thing that you said. Now divide by 3. X plus 2 all over 3 equals y. There's the inverse function. So this inverse function, f inverse of x, is given by x plus 2 all divided by 3. People feel pretty good? So in the first instance, we took this equation and solved it for x, and then switched the y's into x's. In this instance, we switched the y's and x's and then solved for y. Do you think it makes a difference what order we do those two things in? In this case, no. Right, you do all of the same algebra either way. So keep them in whichever order you please. And we'll see examples soon. So let's see a subtlety in the idea of inverse functions. So let's try to invert this function. So let's try to find an inverse to f of x equals x squared. Nice. So that means that I should switch the x's and y's and then try to solve for y. So doing that, switch the x's and y's. I get y squared equals x. If you want to solve that for y, what should you do?
The square root both sides.
Square root both sides. And whenever you square root to get rid of a square, you introduce a plus or minus.
Yep.
So we'll get y equals plus or minus the square root of x. So it looks like f inverse of x is equal to plus or minus the square root of x. Oh, wait, yeah, is there something wrong with that? So this somehow says that, I don't know, let's say x equals 4. That's a number whose square root I know. That says that f inverse of 4 should be 2 and also negative 2. Is something wrong with that? What's wrong with that? If you have a function, yeah.
But doesn't it, well, based on like what you're saying, doesn't it still need to like match like the original function or something like that? So like if it's like positive 4, or no, if it's square root 2 and negative 2, doesn't need to have the same value, or?
It wouldn't pass the vertical line test,
Yeah,
right?
the vertical line test is the problem. I have a single input line to go to 2 places. There are 2 y values corresponding to a single x. A single input is going to 2 different outputs. That's bad. Functions can't do that. This is not a function. This is not a function. So apparently, not every function has an inverse. But which ones do is easy to classify, and it depends entirely on this vertical line test idea. So I'm going to introduce an extra bit of notation. That extra bit of notation will be exactly what functions are involved, have inverses. A function is called one-to-one if every 2 distinct inputs, x values, go to distinct outputs, or y values. So let's think about y equals x squared. Can you think of two not equal to each other x values which have the same y value under this function?
-2 and +2.
-2 and +2 will do the trick. Right, -2 is not equal to +2. So those two are distinct inputs, but they both have an output value of 4. So x equals 2 and x equals -2 both have f of x equals 4. So the squaring function has two different inputs which both go to the same output. So, look at that definition. Is this function a one-to-one function? No. It is not the case that every two distinct inputs go to distinct outputs. There's a counterexample. And just because I'll wind up making this language blunder at some point, there are other words that get used to refer to one-to-one. Sometimes instead of saying one-to-one, I will be lazy and use that abbreviation. Sometimes I'll be fancier than necessary and use the more Latinized word, injective. I'll try to stick to saying one-to-one, but at some point you might see that word in the wild, and it means the same thing as one-to-one. Neat. So, carrying on. Let's talk about one-to-one functions. So here is a function, back to the function. By looking at that function, can you find any two distinct inputs which go to the same output? Yeah, like it's hard to give a name for them because I haven't set it up so that they're obvious things. There's an input, the output is 1. There's an input, the output is 1. There's an input, the output is 1. So, here are 3 distinct inputs, all with the same output. So, would you say that function is one-to-one? No. There are 3 points that violate it. Take a look at the second function. Looking at that second function, can you see any two distinct inputs, so two x values that are not equal to each other, that both give the same output? I think no. So is that function one-to-one, the second one?
Yeah.
Yeah. Awesome. So here's the takeaway. By looking at a graph, you can just read off if a function is one-to-one. A function is one-to-one when the graph of that function intersects every horizontal line at most one point. It's the horizontal line test. So let's use this idea of graphs and what they say about inverse functions to graph an inverse function. So here is a function. By looking at this graph, would you say that function is one-to-one? Yeah. Any horizontal line crosses the graph and at most one point. So let's see what we can say about the inverse function. So here is the graph of the original function. We'll pay attention to 3 special points. And I'll use those 3 special points to say something about the inverse. So, let's answer a few questions using this graph. Can you find, by looking at that graph, an x value that results in f of x equals 3?
So when the y value is 3.
A place where the y value is 3. Yeah. So what x value gives you a y value of 3?
-2.
You're a -2. Very good. Nice. So that means this function f has the property that f of negative 2 equals 3. An input of negative 2 results in an output of 3. So by reading that, can you tell me what f inverse of 3 is?
-2.
Negative 2. And maybe the takeaway there, just to say it explicitly, f of negative 2 equals 3 means f inverse of 3 equals negative 2. Inverse functions switch inputs for outputs. So let's go ahead and graph this. So that means 3, negative 2 must be on the graph of the inverse function. 3, negative 2. So let's play the same game a few more times. Let's try to figure out what f inverse of 1 is. So, first things first, can you find me an x value which gives you f of that x value equals 1?
-1.
Right here on negative 1? Oh, is this like Archivas? No, Popper. F of negative 1 equals 1. So, what can you tell me about f inverse of 1 then?
X equals 1, and you get the output is 1, then create in for the opposite, which that'll be the opposite, where for the inverse of 1 will equal -1. Or,
Yeah. So f sends an input of 1 to negative 1. Inverse function switches inputs and outputs. F of 1 is negative 1. 1, negative 1 will be on the graph of the inverse function. 1, negative 1 is on the graph of the inverse. And let's do this twice more. So if I look at this, tell me, what is f inverse of 0? Are you all 1? Is that people happy?
yeah.
Nice. So maybe you see the pattern here. F inverse of 0 equals 1. So that tells you 0, 1 is on the graph of the inverse. And finally, what's f inverse of negative 3?
+2.
Positive 2. So negative 3, 2 is on the graph of the inverse. And now, well, if you look at this graph, it's all piecewise linear, so will the inverse be. So, what's the point? So we've graphed an inverse function. Let's now think about how we actually graph that. So this pinpoint down here at 3, negative 2, it came from the pinpoint way up there at negative 2, 3. Those are like exactly the same point though, right? Just the x's and the y's are switched. There's the takeaway of this bit, not this exercise. If you have the graph of a function, you can get the graph of the inverse function by swapping x values with y values.
If you move the sheet.
Oh yeah, sorry about that. If you want to get, if you have a one-to-one function, you would like the inverse to just swap all the x and y values on the graph. That makes sense? And it's reasonable if you just think about what switching inputs and outputs means. Inputs are x values, outputs are y values. Nice. Maybe I'll phrase it one additional way. You can also get it by flipping, it's reflecting over the line y equals x. Any questions so far? So here's what's going to happen with the rest of this time. I'm going to involve one more function. We'll say a few more things about graphs, and then we'll wax a little bit technical with what inverse functions really mean. So let's proceed. Let's find the inverse function to this function. So let's set up the thing that we need to solve. If you need to find that inverse function, what equation do you need to solve? You want to like switch the x's and y's and then solve for y. Or just solve for x and then switch the x's and y's. But let's do it this way. All right, so I'll take x minus 1 over x minus 2 equals y. I'll swap all the x's and y's to get the equation y minus 1 over y minus 2 equals x. And I'll solve for y. All right, so one of two options. I can talk through some algebra with some guidance from you, or I can be quiet for a bit, you can do the algebra, and then we'll come together. People want me to talk through some algebra? Any demand for me doing algebra? Okay, I did not see any hands go up, so I'll be quiet for a little bit. Consult with those around you if you want. Solve this equation.
Can you ever do this, or you ever do this, or you look at it?
Solve for y.
Explain this kind of shortcut. So since you're dividing here, since so it's x minus 1 over x minus 2, so you switch this x, right?
Yeah.
And then
Well, design, you don't necessarily switch. Because that's like when you have like the, that's like when you have like the, when you have like the eyes and the imaginary numbers.
no, I don't remember the specifics. This is this the correct equation or no? No. Okay.
And because if you're switching with the, yeah, if you're switching with the eyes, then it'll make more sense.
Let's try to come together a little bit and just at least get a good boss unit. So the thing that's annoying about this equation is there's a fraction on the left-hand side. What can you do to make it so there's not a fraction on the left-hand side?
I'll divide the denominator on this more sides together. So.
Yeah, you can do this, play this game called cross multiplication. So multiply the other side by the denominator of the 1. So if you do that, you will get this. Y minus 1 equals x times y minus 2. So now I'll see how people are feeling again. I can continue talking through it. Okay, this time heads actually nodded. Okay. So let's do it. What seems like a good next move? I want to get y on its own. What seems like something that's reasonable to do here?
Distribute the x into y minus 2.
Nice. Let's do that. So y minus 1 equals xy minus 2x. That seems like, well, maybe it's not so clear as formula, but that's something. You can always just keep on following your nose and like doing an algebraic manipulation and hope that you eventually get somewhere nice. And if it takes you too long, then probably that means you've screwed something up and missed something. But let's keep on going from here. What seems like, we want to get y on its own, so what seems like a good philosophy to follow from here?
Subtract negative xy from that side and just do that to the same side.
Subtract that to the other side, so get all the y's on the same side. That seems not unreasonable. let's subtract xy to the other side. So I'll see y minus xy, doesn't matter where I put it, minus 1 equals minus 2x. All right, all the y's are now on the same side.
After that, just add one to the other side.
Get the thing that doesn't have any y's onto the side that has things that don't have any y's. Y minus xy equals 1 minus 2x. Have I screwed anything up yet? All right. Okay, so now everything on the left-hand side has a y next to it. Yeah,
Can you factor out the y?
let's factor out that y. So that'll be y times 1 minus x equals 1 minus 2x. Nice. And with that in mind, how would you now get y onto its own?
You just divide the 1 minus x and from both sides.
Divide the thing that's next to the y over to the other side. Y equals 1 minus 2x over 1 minus x. Great. Have we got y onto its own? Yeah.
Will it be okay if we just like wrote -2 times x plus 1 over 1 minus x?
Without showing any intermediate steps
No,
whatsoever?
it's just like same steps, but like if we wrote down -2x plus
Oh.
1.
Sure, yeah, that is the same. So for either of these answers, I will have the same objection.
Okay.
They're both not quite as simple as they could be. Right, like if you saw -5 divided by -6, how would you rewrite that? 5, 6, right? So you can multiply and divide by -1.
Okay.
I see a polynomial divided by a polynomial. The biggest piece of each polynomial is negative. So maybe I'll multiply the top and bottom by -1 and try to make it simpler. It's not a big simplification. I think it's one worth making though.
Okay.
So distribute the -1, that'll become 2x minus 1 over x minus 1. Nice. So apparently there is f inverse of x. How do people feel about that? Does that seem reasonably okay?
Good.
So, in order to have a sales pitch for an extra credit problem, do you think we could have done that for basically anything that looks like linear function divided by linear function? Extra credits, do that for absolutely any function that looks like linear function divided by linear function. Get a formula for what the inverse to a fractional linear transformation is.
What type of linear function are you talking about? Like any type of linear function or maybe a little bit?
Yes. For any unknown constants, A, B, C, and D, find the inverse to that. So your end result will have some A's, B's, C's, and D's in it. The upshot is, if you ever, once you get that formula, you can use that formula and just know what the inverse to one of these functions is. So let's go back to thinking in terms of graphs. So my end goal is going to be the theorems down here where I say what the domain and range of an inverse function is. So let's remember how to find domains and ranges from graphs. So if you have some function f of x whose graph you have in front of you, what is the domain of that function? And maybe it's best to like ask in a specific case. There's the graph of a function. What's the domain of that function? Nice. How did you read that up?
The arrows and what do you mean? How do I read it up?
Kind of. Sorry, like you have the answer. I just phrasing the question wrong. You read off all the x values that are on the graph.
Yeah.
Yeah. So there's how you read off the graph of a function. That's all I'm trying to go for in that line. The graph of a function tells you the domain. The domain is all x values on the graph. And now that I've written that down, you definitely know what's going to go on the next space. If you have the graph of a function, how can you read off the range of a function?
All y values on the graph.
By a thing that's written on a previous page, how do the graphs of a function and the inverse of that function differ?
X values are the y values, the y values are your
Yeah, x and y values. Let's switch. So let's make a quick string of sentences in order to answer this question. What is the domain of the inverse to a function? So let's try to compute the domain of an inverse function. So it's, yeah.
Would it be all the y values?
Yes. So I'm going to write like a few bullet points, and that's what the second bullet point is going to be. Because what is the first bullet point? The first bullet point is that's all x values on the graph of f inverse. But now we can say what you said, right? All the x values on the graph of the inverse, that'll be the same as all the y values on the graph of the original. All y values on graph of f. And there's one last bullet point. All the y values on the graph of f. What is that? The range of f. And there's nothing mysterious about it. There's the full argument. Let f be a one-to-one function. The domain of the inverse function, f inverse of x, is the same as the range of f. So what do you expect the range of the inverse function is probably the same as? Same as the domain of f. Nice. So let's try to connect that for the example that's at the top of the page, and then maybe we'll look at a graph and do some. I don't need to. So here's a function. The function that we inverted earlier. I'll write down the inverse. The inverse is allegedly 2x minus 1 over x minus 1. The only thing not in the domain of this function is the vertical asymptote. Where's the vertical asymptote of that function? X equals 2. So the only thing not in the domain is 2. The only thing not in the range of that function is the location of the horizontal asymptote. Where is the horizontal asymptote of that function? It is at 1. We found the inverse function to be this. Looking at that graph, what is the only thing not in the domain?
Probably one.
1. I'm doing this in the opposite order from how the paper does. Okay. So that should mean the only thing not in the domain of the inverse is this. The only thing not in the range should be y equals 2. And let's just check if that's right. And now say what you said. Where's the vertical asymptote of this? 1. So 1 is not in the domain. Check that. Where is the horizontal asymptote? 2. So 2 is not in the range. those ideas make sense? So the last thing that I want to do is I want to give the technical definition of what the inverse function actually means. And if you want to verify that definition, we'll walk through that. So, for any function f, the inverse, f inverse, is the unique function that satisfies that this composition, f inverse of f, is equal to x. And f inverse of x is equal to x. Whenever you take an x value that's in the appropriate value. So there's the definition of what the inverse function actually is. So if we actually believe that the inverse of this function is that, we need to be able to check those two compositions and see that they actually both give x. So on the next page, what are we going to do? We are going to check that this function actually has this as its inverse. So let's go ahead and do that. 2x minus 1 over x minus 1. So let's try to check that the inverse of this function is actually that other function. And we have to do that by computing some composition. So that's exactly what we're going to do. Let's try to compute the composition of these two functions. To do this, we must compute f of f inverse of x and f inverse of f of x. And I think we have enough time to do one of the two, but not both. And so I'll ask you all which one you would like to do all together right now. F of f inverse or f inverse of f? The first one? 4 hands. Second one? More than 4 hands, but I think you may have put your hand up twice. Did you? Okay. We'll do the second one then. Let's do this one. Let's try to compute that. So let's try to compute f inverse of f of x. And I'm going to try to use this color coding to help me do the composition. So there's the piece that's colored in pink now. So I guess that means that, so what does function composition mean? That means I need to take the formula for f inverse of x, replace all the x's with the thing in pink. So I'll do that over the course of 2 steps because otherwise I'll do something wrong. So the formula for f inverse is in purple. That's 2 times x So far, so good. Do I have a formula already for f of x? Yeah, so now I'll plug that in. Equals 2 times x minus 1 over x minus 2 minus 1, all divided by x minus 1 over x minus 2 minus 1. Yeah, okay. Cool. So that looks kind of complicated. But complicated just means we can do some simplification. If it already looks simple, then we wouldn't have anything to do and we would have difficulty proving that this thing is actually equal to x. So, in looking at that, what seems like some simplification? What would you want to do to this? Say again? Let's multiply that 2 into the fractions. That means that the top will get multiplied by 2. So I'll get 2x minus 2 over x minus 2 minus 1 over x minus 1 over x minus 2 minus 1. Cool? you want to do next? That seems reasonable. I'll multiply the top of the fraction and the bottom of the fraction by x minus 2. And maybe I'll do a bit of motivation. The reason that seems like a good idea is that'll at least get rid of a fraction, right? When I do the distribution, some stuff will become nicer. So let's do the distribution. Maybe this is a step you wouldn't take, but I'll add this step in. 2x minus 2 divided by x minus 2 times x minus 2 minus 2x minus 2 all over x minus 1 over x minus 2 times x minus 2 minus, oops, that's supposed to be this cutoff. That's better. All right, and the whole point of this move is you see something that cancels, right? What cancellation do you see? Those two can cancel? All right, so let's cancel those. Is there another cancellation that you see? Same thing on the bottom. So right, whenever you see something divided by a thing and then immediately multiplied by that same thing, those things will cancel. All right, so with those cancellations, maybe I'll just write down what we have again. Equals 2x minus 2. That's illegible. X minus 2. Maybe I'll do one more thing in this step. I'll also distribute that minus sign through those parentheses. Minus x plus 2 all over x minus 1. And I'll do the same distribution in the bottom. Minus x plus 2. All right.
Can you move the piece of paper out?
Oh, yeah, sorry about that. All right, so what do you see there that cancels or simplifies or combines or something? Yeah, okay. No need to beat around the bush about it. You wind up with just x on the top, 1 on the bottom, when you do the various simplifications to get there. Huh, is that exactly what you needed to get? So we have lost track of the forest for the trees then. If you want to show that a thing is actually an inverse, you need this to always be equal to x. Did we get it equal to x? Yeah, so if you like, well, halfway done, to really complete the argument that this is the inverse, do it again. Neato. Now you'll put it okay. So, if that felt particularly okay, then you definitely should do the extra credit associated with today, because that manipulates most of the law.
Thank you.
Have a good day.
I have a quick question about the answers.
Yes.
So on the last problem, if you didn't use a calculator, you got